Very good morning to all dear students of MSc Final class. In the last lecture, dear students, I told you that whenever the potential height is considered to be infinity and the width of the potential well is taken as 0, tending to 0, then the product V0B remains constant in the Kronig Penney model. This equation we did obtain earlier. And then I told you that in this case of delta function potential, we come across a very simple value of P equals to MA into V0B upon H cross square, where the symbols have their usual meaning. V0 into B is of course the product of, it must be finite because V0 tends to infinity and B tends to 0. So the product remains finite, and this equation is defined as the Kronig Penney equation. And the value of P has a certain physical interpretation. Suppose P is equal to 0 in any particular potential problem. If we consider P equals to 0, it means from this equation number 10, that is here, if I take P equals to 0, then cos alpha A will be equal to cos Ka. It means alpha A will be equal to, so in this particular case I can say that cos alpha A is equal to cos Ka and alpha A equals to K. So I shall obtain, I can write down the value of alpha, that is root 2 ME upon H cross square equals to K. So definitely E will be equal to H cross square K square by 2M. And these are the free particle. This is the energy of a free particle. We all know H cross K denotes the linear momentum, and you can easily understand that kinetic energy E equals to half mv square, that is m square v square by 2m, dividing and multiplying by m. mv is momentum, so it is p square by 2m. This is kinetic energy of a free particle, and we all know in quantum mechanics P equals to H cross K. K is the wave propagation constant, so E will be equal to H cross square K square upon 2m. This is what we obtained here. So E equals to H cross square K square by 2m, and that is the case of free particle solution. If P tends to infinity, then you know P tends to infinity, then of course if this tends to infinity, then the value of sine Ka must be equal to 0. And in that case, dear students, you know, value of sine theta is 0 for theta equals to 0, pi, 2 pi, and so on, minus pi, minus 2 pi, and so on. It means theta must be equal to plus minus n pi, where n is an integer 1, 2, 3, 4. 0 can also be included. So in that case, I will get alpha equals to plus minus n pi, and alpha square is equal to n square k square by a square, and I will get E equals to n square h square upon 8 ma square. This is the energy for a electron bound in an infinite potential box, which you have read in your undergraduate classes, that whenever a particle is bound in an infinite potential well, then the energy eigenvalues of it are quantized, and it can't have continuum of energy. It can have h cross square upon 8 ma square, it can have 2h cross square upon 8 ma square, it can have 9h cross square upon 8 ma square, etc. And why this sin alpha equals to 0? You can understand from here that for this relation to be finite, if p tends to infinity, then the coefficient sin alpha must go to 0. So whenever potential p increases, whenever the term p increases, the area of the potential barrier increases, you can see. And when p tends to 0, then all the bound vanishes and the electron behaves like a free electron. This is what you have to understand. This is the physical significance of quantity p. Now if I plot the left hand side, that is p upon alpha into sin alpha plus cos k, that is here, as a function of alpha a. See, the right hand side consists of only one term, that is cos ka, and we all know that value of cos theta or sin theta always remains in between +1 and -1. So value of cos theta remains in between +1 and -1. In this way, I can say that if I plot the left hand side, which is obtained as a curve like this, then only those values are allowed which remains between +1 and -1. So I draw two lines corresponding to +1 value and -1 value. Now you see, these are the allowed values. So from here to here, this is allowed band, and from here to here, the shaded one is forbidden. These values of alpha a are not possible for the electrons in the potential value. The shaded values are not possible, I tell you, because this value goes outside the 1 mark, this goes below the -1 mark, up above the +1 mark, minus. So these shaded values are continuously, of course alpha a is increasing, but one thing you can see, this width is decreasing. At alpha a equals to 0, the width was maximum, then it got smaller and smaller and smaller. This is what I am going to discuss. So we can understand this particular, see, because cos Ka can have any value between -1 to +1, the left hand side can vary between -1 to +1. The value of alpha a here, the value of alpha a for which this value becomes greater than +1 are defined as forbidden. Mean they are not allowed. Now important conclusions of this particular model we can have. See, first one is the energy spectrum of electron has a large number of allowed energy bands separated by forbidden energy band. These forbidden bands are called energy gap. Here it is. The shaded part defines forbidden gap. Then the width of allowed energy bands increases with increasing alpha a, and this is what I told you, that this allowed energy band width increases, but that of the forbidden at the same time decreases. Here see, smallest larger, and due to, you can say, by tracing, this must be a bit large, and so on. And you can see it is the broadest one, then the width goes on decreasing, smaller and smaller. Now one more conclusion, you can continue with it. With increasing